Welcome to this coding walkthrough. Today, we'll be tackling problem number 873, length of longest Fibonacci subsequence. This problem is an excellent opportunity to explore dynamic programming techniques and improve your understanding of sequence-based problems. Let's dive into the details and work through it step by step. The Fibonacci sequence is a well-known mathematical sequence where each number is the sum of the two preceding numbers, starting with 0 and 1. For example, it begins as 0, 1, 1, 2, 3, 5, 8, and so on. In this problem, we are given a strictly increasing array of positive integers, and our goal is to find the length of the longest subsequence within this array that follows the Fibonacci-like pattern. A subsequence means that we can pick elements from the array in the same order, but not necessarily consecutively. If no Fibonacci-like subsequence exists, we simply return 0. The input format specifies that the array will be sorted in strictly increasing order, and the output is an integer representing the length of the longest valid Fibonacci-like subsequence. To help clarify the problem, let's look at an example. Suppose the input array is 1, 2, 3, 4, 5, 6, 7, 8. The output for this input is 5. This is because the longest Fibonacci-like subsequence in the array is 1, 2, 3, 5, 8. Notice that each number in this sequence is the sum of the previous two numbers, and the order of elements matches the order in the original array. The subsequence has a length of 5, which is what we return. Now consider another example with the input array 1, 3, 7, 11, 12, 14, 18. For this input, the output is 3. The longest Fibonacci-like subsequence here is 1, 11, 12. This sequence satisfies the Fibonacci-like property because 1 plus 11 equals 12, and the numbers appear in the correct order within the array. The length of this subsequence is 3, which becomes the result. For a third example, the input array is 1, 2, 3, 4, 9, 10, 11, 12, 22, 33. The output for this input is 4. The longest Fibonacci-like subsequence in this case is 1, 2, 3, 5. Again, each number is the sum of the two preceding numbers, and the order of elements in the subsequence matches their order in the original array. Moving on to the constraints, the input array will have a length between 2 and 1000, and each element will be a positive integer less than 10 to the power of 9. The array is guaranteed to be sorted in strictly increasing order, which means no duplicate elements are present. When thinking about edge cases, there are a few important points to keep in mind. First, if the input array has fewer than 3 elements, the output is always 0 because it's impossible to form a Fibonacci-like sequence with fewer than 3 numbers. Second, if no Fibonacci-like subsequence can be found, we simply return 0 as the result. Third, arrays containing very large numbers must account for the fact that summing 2 elements could cause overflow, so we need to handle this carefully. Lastly, since the array is strictly increasing, any input with repeated elements is invalid and will not be considered. To start, let's consider the brute force approach. The intuition here is simple. We iterate through every possible pair of numbers in the array as the first 2 elements of a potential Fibonacci-like sequence. For each pair, we attempt to extend the sequence by repeatedly checking if the sum of the last 2 elements exists in the array. This process continues until no further elements can be added. At the end, we return the length of the longest sequence found across all pairs. The key observation that makes this approach valid is the property of Fibonacci-like sequences. Any valid sequence must satisfy the relationship a k equals a I plus a j, where I j and k are indices such that I less than j less than k. This means we can systematically construct all possible sequences by trying every pair of starting numbers and extending them. However, the brute force method comes with significant limitations because of its computational cost. Specifically, it has a time complexity of n cubed, as we need to evaluate n squared pairs, and for each pair, searching for the next element in the array takes n. The space complexity is minimal at 1, but this comes at the expense of efficiency, making it impractical for larger arrays. The brute force approach, while conceptually straightforward, fails to take advantage of potential optimizations from repeated subproblems. This is where the dynamic programming approach comes into play. With dynamic programming, we use a hash table to track Fibonacci-like subsequences. The hash table, referred to as DP, stores pairs of numbers A, J, A, I as keys and the length of the longest Fibonacci-like subsequence ending with these two numbers as values. This structure allows us to efficiently extend sequences without redundant recomputation. The fundamental observation remains the same. For a valid Fibonacci-like subsequence, a k must equal a I plus a j for indices I less than j less than k. If a k exists in the array and the pair a j a I is already tracked in DP, we can extend the sequence by updating the length for the new pair a j a k. The transition relation for this update is straightforward. DP a j a k equals DP a I a j plus 1. Initially, every pair of numbers starts with a base case length of 2. To implement this, we first create a hash table index to map array values to their indices for efficient lookups. Then, for each pair a j a k with j less than k, we compute the potential preceding value a I equals a k a j. If a I exists in the array and its index is less than j, we update the hash table accordingly. Throughout this process, we keep track of the maximum sequence length found and return it at the end. This approach drastically reduces the time complexity to O(n squared), as we now iterate through all pairs and perform O(1) operations for each, while the space complexity is O(n squared) due to the storage required for the hash table. The dynamic programming approach offers significant advantages over the brute force method. By efficiently handling repeated computations, it eliminates redundancies and ensures that we only focus on valid subsequences. The use of hash maps allows for O(1) access and updates, making the algorithm well-suited for larger inputs. The key insight here is that Fibonacci-like subsequences can be represented as pairs in the hash table, enabling efficient tracking and extending of sequences. With this optimization, we achieve a practical and scalable solution. Ultimately, the dynamic programming approach is chosen because of its superior performance in terms of time complexity, which is O(n squared), compared to the O(n cubed) of brute force. However, it does come with a trade-off. While the brute force method uses constant space, the DP approach requires O(n squared) memory to store the hash table. This trade-off is justified given the substantial reduction in computation time. Conceptually, brute force might be simpler, but for competitive programming or real-world applications with larger datasets, the dynamic programming solution is far more efficient. In conclusion, this strategy strikes the right balance between efficiency and scalability, making it the preferred method for solving the problem. To solve the problem of finding the length of the longest Fibonacci-like subsequence in an array, we start by understanding that a Fibonacci-like sequence follows the rule A plus B equals C, where A and B are consecutive elements, and C is the next element. The first step in our approach is input validation. If the length of the array is less than 3, we immediately return 0 because it's impossible to form a Fibonacci-like sequence with fewer than 3 numbers. Next, we use a hash set to store all the elements of the array. This allows for constant time membership checks, which are critical for efficiently verifying if specific numbers exist in the array. Without this optimization, we'd need to repeatedly iterate through the array, leading to unnecessary computational overhead. Now, we move on to iterating over all possible pairs of array elements. This is done using two nested loops, where the outer index runs from the first element to the second to last, and the inner index starts just after the outer index and runs to the end. For each pair of numbers, we initialize a potential Fibonacci-like sequence. The first two numbers in the sequence are the pair itself, so we set A and B to these values and initialize the sequence length to 2. After this, we try to extend the sequence. The next number in the sequence, C, is calculated as the sum of A and B. If this C exists in our set, we extend the sequence by updating A to B, B to C, and increasing the sequence length. If C is not in the set, we break out of the loop because the sequence can no longer be extended. Once the sequence for a given pair is fully processed, we update our global maximum length if the current sequence length is longer. Finally, after iterating through all pairs and calculating the length of the longest Fibonacci-like sequence for each, we return the result. If the global maximum length is greater than 2, we return it as the result. Otherwise, we return 0 to indicate that no Fibonacci-like sequence was found. There are several key insights to note here. Using a hash set for lookups is a major optimization that avoids redundant checks and improves performance significantly compared to a naive approach. By iterating over all pairs of numbers, we ensure that no potential starting points for sequences are missed. The algorithm also includes an early termination condition. If C does not exist in the set, we stop extending the sequence, which saves valuable computation time. Additionally, the algorithm is designed to handle edge cases well, such as arrays that are too short, arrays with no valid sequences, or arrays with duplicate numbers. For data structures, the hash set is the backbone of our solution, while variables like A, B, and C help track the sequence being processed. The current sequence length and the global maximum length ensure that we can efficiently manage and update our results. In terms of complexity, the time complexity of the algorithm is O, n squared asterisk k. The nested loops contribute the O, n squared factor because we are iterating over all pairs of elements. The k factor represents the average length of the Fibonacci-like sequences we check, as extending the sequence involves iterative calculations. For space complexity, the algorithm requires O, n, space for the hash set used to store the array elements. This space allows us to perform quick lookups, which are critical for the efficiency of the solution. Overall, the algorithm balances time and space efficiency effectively, making it a practical approach for solving this problem. This implementation solves LeetCode problem 873, length of longest Fibonacci subsequence, efficiently using dynamic programming and a hash map for memoization. The goal is to find the longest Fibonacci-like subsequence in the input array. We begin by checking if the array length is less than 3, as a Fibonacci-like sequence requires at least 3 numbers. If this condition is met, we return 0. Next, we define a dictionary DP to store the maximum length of Fibonacci-like subsequences ending at specific indices, j, k. We also create an index dictionary to map each number in the array to its index for quick lookups. The main part of the algorithm involves nested loops. For each pair of indices, j, k, or j less than k, we calculate the difference ARR, k, RR, j, which represents the potential previous number in the Fibonacci sequence. If this difference is less than ARR, j, to ensure the sequence is valid and exists in the index dictionary, we retrieve its index I. Using dp.get I, j, 2, plus 1, we calculate the length of the Fibonacci-like subsequence ending at j, k. If there is no prior sequence ending at I, j, we assume a default length of 2. We update dp j, k with this value and also maintain max_len to track the overall maximum length. Finally, after processing all pairs, we return max_len, which contains the length of the longest Fibonacci-like subsequence found in the array. The algorithm has a time complexity of O, n squared, making it efficient for moderately large input arrays. Here, we begin our Java implementation of finding the length of the longest Fibonacci subsequence. First, we import the necessary libraries and define our solution class. Inside the lenLongestFib subsec method, we start by checking if the input array has fewer than 3 elements, as it's impossible to form a Fibonacci-like sequence with less than 3 numbers. Next, we create a hash map called dp, which will store the lengths of Fibonacci-like subsequences ending at specific pairs of indices. We also prepare another hash map called index to map each value in the array to its corresponding index, making it quick to find the position of any number during our calculations. After populating the index map, we initialize a variable maxlen to track the maximum length of any Fibonacci-like subsequence we find. Now, we use 2 nested loops to iterate through all pairs of indices j and k, where j is less than k. For each pair, we calculate the difference between the 2 numbers, which represents the potential previous number in the sequence. To ensure the sequence is valid, we check if this difference is smaller than the current number at j and whether it exists in the index map. If both conditions are met, we retrieve the index of this difference, which we refer to as I. At this point, we update our dp map. We construct a key using the indices I and j, which represents the subsequence ending at these 2 indices. Using this key, we retrieve the length of the existing subsequence from dp, defaulting to 2 if it doesn't exist yet. We then calculate the new length by adding 1 to this value and store it in the dp map under the key for the current pair of indices j and k. During this process, we also update maxlen to ensure that it always holds the length of the longest Fibonacci-like subsequence found so far. After iterating through all pairs of indices, we return maxlen as the result, which represents the length of the longest Fibonacci subsequence in the input array. This implementation ensures that we efficiently track and update subsequences using dynamic programming and hashing, making it well suited for this problem. In this problem, we are tasked with finding the length of the longest subsequence in a given array that behaves like a Fibonacci sequence. A Fibonacci-like sequence follows the property that each number is the sum of the two preceding numbers, and the indices of these numbers must satisfy the condition I less than j less than k. To understand this, let's look at the first example where the input array is 1, 2, 3, 4, 5, 6, 7, 8. The length of the array is 8, so we initialize n to 8. Next, we set up an empty dictionary called dp to store the lengths of Fibonacci subsequences ending at specific pairs of indices. We also create an index mapping to quickly access the position of any value in the array. This mapping is 1 o'clock, 2, 1, 3, 2, 4, 3, 5, 4, 6, 5, 7, 6, 8, 7. Finally, we initialize max_len to 0, which will track the length of the longest Fibonacci subsequence we find as we process the array. Now, we start iterating through pairs of indices to identify Fibonacci-like subsequences. For k equals 2, the current value ARR, k, is 3. We then consider j equals 1, where ARR, j, is 2. To check if these two numbers can extend a Fibonacci sequence, we calculate the difference diff equals ARR, k, ARR, j, which is 1. Since diff is less than ARR, j, and exists in our index mapping, we find that I equals index, diff, gives us 0. This means the numbers at indices 0, 1, and 2 specifically, 1, 2, 3, form a valid Fibonacci subsequence. We then update dp 1, 2 to be dp.get 0, 1, 2 plus 1, which evaluates to 3. This indicates that the subsequence ending at indices 1 and 2 has a length of 3. We also update max_len to 3. Repeating this process for other pairs, such as k equals 3 and j equals 2, allows us to find longer subsequences like 1, 2, 3, 5, 8. By the end of this iteration, max_len is updated to 5. We then return this value as the length of the longest Fibonacci subsequence for this input. Let's move to another example where the input array is 1, 3, 7, 11, 12, 14, 18. The initialization process remains the same. We set n to 7, create an empty dp dictionary, and map each value in the array to its index. This gives us index equals 1 o'clock, 3, 1, 7, 2, 11, 3, 12, 4, 14, 5, 18, 6, and we initialize max_len to 0. As we iterate through pairs, we come to k equals 4, where ARR, k, is 12. For j equals 3, ARR, j, is 11. We calculate diff equals ARR, k, ARR, j, which is 1. Since diff is less than ARR, j, but does not exist in our index mapping, this pair cannot extend a Fibonacci-like sequence, so we skip it. Later, for k equals 6 and j equals 4, we find a valid subsequence, 7, 11, 18. By updating dp and max_len accordingly, we determine that the longest Fibonacci subsequence in this array has a length of 3. This result, max_len equals 3, is returned. Finally, let's consider the input array 1, 3, 5, 9, 10, 11, 14, 16, 20. Again, we initialize n to 9, set up an empty dp dictionary, and create an index mapping 1 o'clock, 3, 1, 5, 2, 9, 3, 10, 4, 11, 5, 14, 6, 16, 7, 28. We start with max_len set to 0. As we iterate, for k equals 8 where ARR, k, is 20, we consider j equals 7 where ARR, j, is 16. Calculating diff equals ARR, k, ARR, j, gives us 4. Since diff is less than ARR, j, and exists in the index mapping, we identify a valid subsequence, 4, 16, 20. By updating dp and max_len, we determine that the longest Fibonacci subsequence here has a length of 3. To summarize, this solution uses dynamic programming with a hash map to efficiently track and extend Fibonacci-like subsequences. The nested loops make the time complexity O, n squared, and the dp dictionary contributes to a space complexity of O, n squared. This method ensures that we can identify the longest Fibonacci subsequences in a given array with optimal efficiency. Here, we analyze the time complexity of our solution. The overall time complexity is n squared, where n is the length of the input array. To break this down, the first step is the initialization of the index dictionary. This dictionary is constructed by iterating through the array once, assigning each unique element as a key and its index as the value. Since this involves a single pass through the array, it takes n time. Next, we have the nested loops. The outer loop iterates through the array, running n times. For each iteration, the inner loop processes all prior indices, meaning it runs up to k times for each iteration of the outer loop. When you sum up all inner loop iterations for every k, it forms a series, 1 plus 2 plus 3 plus n1, which simplifies to n1/2. This is a quadratic growth, leading to n squared. Together, these operations dominate the time complexity of the solution, making it n squared. Continuing with the time complexity, we also consider the dictionary operations involving dp. Inside the nested loops, we compute the difference diff, check if it is valid, and update the dp dictionary. Each dictionary operation, such as lookup, retrieval, or update, has an average time complexity of 1. Since these operations are performed during each iteration of the nested loops, their contribution to the overall complexity is n squared. Thus, the nested loops remain the dominant factor, confirming the total time complexity is n squared. Now, looking at space complexity, the solution requires n squared space in total. First, the index dictionary stores each unique number in the array as a key, along with its index as the value. Since the dictionary size is proportional to the number of elements in the input array, it takes n space. The second contributor to space complexity is the dp dictionary. This dictionary stores pairs of indices, j, k, as keys, with the length of the Fibonacci-like subsequence ending at those indices as the value. In the worst-case scenario, every pair of indices, j, k, where j less than k could be stored in dp. The total number of such pairs is n1/2, which simplifies to n squared. Additionally, variables like max_len and the loop indices I, j, and k require constant space, 1. Since the dp dictionary is the largest contributor, the overall space complexity is dominated by it, resulting in n squared. Now let's compare this optimized solution to the naive or brute force approach. A naive approach would involve generating all possible subsequences of the array and then checking each one to determine if it satisfies the Fibonacci-like property. Generating all subsequences has a time complexity of 2 to the power of n, and verifying each subsequence would add further processing time. This makes the naive approach exponentially slower than the optimized solution. In contrast, the optimized approach uses dynamic programming and a dictionary to efficiently store and retrieve the lengths of Fibonacci-like subsequences. By focusing only on valid indices and updating the dp dictionary efficiently, it avoids the overhead of explicitly generating and checking all subsequences. This improvement reduces the time complexity to n squared. Finally, let's examine the best, average, and worst-case scenarios for this solution. In the best case, the input array contains no valid Fibonacci-like subsequences. Even in this case, the nested loops still run for all valid indices, so the time complexity remains n squared. In the average case, the input array contains a mix of valid and invalid subsequences. Here, too, the number of iterations is determined by the nested loops, so the time complexity is still n squared. In the worst case, every pair of indices, j, k, forms a valid Fibonacci-like subsequence. Even then, the algorithm performs n squared operations due to the nested loops, and the space complexity is also n squared, because all pairs are stored in dp. To mathematically confirm our big O bounds, the nested loops iterate n*(n1/2 times, which is quadratic. Similarly, the dp dictionary can store at most this many key value pairs, confirming both time and space complexities as n squared. When tackling this problem, there are several common mistakes to watch out for. First, not handling edge cases for the array length is a frequent issue. If you assume the array always has at least 2 elements, you might run into runtime errors with smaller or empty inputs. Always validate the size of the input array upfront. Another mistake is misinterpreting the problem constraints. For instance, since the problem involves distinct numbers and arrays can be as large as 10 to the power of 4, ignoring these details can lead to inefficient or incorrect solutions. Next, brute force approaches often involve generating all possible pairs using nested loops, but this can result in time complexities of n cubed, or worse, which are impractical for larger arrays. Finally, when using dynamic programming, maintaining the DP table correctly is critical. Failing to reset or initialize the table properly can lead to stale values or incorrect transitions, causing your solution to produce the wrong results. Another pitfall is not focusing on the requirement to find the longest Fibonacci-like subsequence. It's not enough to just find any valid subsequence, you need to ensure it's the longest possible. Missing this detail can lead to incomplete solutions. Now, let's consider some interview insights. One key skill is recognizing patterns, such as identifying that the sum of two numbers should match a third. Spotting this relationship early can guide you toward efficient solutions using a hash table or dynamic programming. Additionally, interviewers may ask you to compare different approaches, like brute force versus hash-based methods or DP. Be prepared to discuss trade-offs in terms of time and space complexity. Explicitly addressing edge case handling, such as empty arrays or arrays with no valid subsequences, is another way to demonstrate thoroughness. Lastly, iterative optimization is often encouraged. Starting with a simple brute force approach and progressively refining it shows your ability to adapt and improve your solution under time constraints. This problem is closely related to other sequence-based challenges on LeetCode, such as the longest increasing subsequence, longest arithmetic subsequence, and longest string chain. Exploring these problems can help you identify common strategies and patterns that apply across them. Now, let's look at alternative approaches to solving this problem. The hash table approach is a powerful method, combining pair sums with hash maps to enable faster lookups. This achieves a time complexity of n squared, but requires additional space for the hash table. It's a great choice for mid to large input sizes where brute force becomes infeasible. On the other hand, dynamic programming is another effective strategy. By using a DP table to track Fibonacci-like subsequences, you can systematically handle state transitions and ensure correctness. This approach is especially useful when the problem emphasizes tracking the length of subsequences. Finally, brute force serves as a baseline approach. While it's simple to implement, it's computationally expensive, often resulting in n cubed, or worse time complexity. This method is best suited for small input sizes or as a stepping stone to more optimized solutions. Starting with brute force can help you understand the problem structure before transitioning to more efficient approaches like hash tables or dynamic programming. Balancing simplicity and efficiency is key, and knowing when to use each method will make your solution both effective and adaptable. Great job making it to the end. Today, we explored how to solve the length of longest Fibonacci subsequence problem using dynamic programming techniques. We reviewed the approach, its complexity, and the key concepts that make this solution efficient. Thanks for watching, and don't forget to like, share, and subscribe for more problem-solving content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!